All right, thank you, Fadil, for the kind introduction, and thank you for attending my talk. So today I will discuss some of our recent work towards leveraging foundation models to boost the performance of physical AI systems in general, with a focus on autonomous vehicles, along with tools and techniques to enable the safe deployment of such systems. And as I said, the focus will be on AV systems, but many of the techniques and tools that I'll be mentioning apply more broadly to general robotics. Now, the premise of this talk is that the foundation models provide key opportunities to accelerate the development of autonomous robotic systems. To be more specific, by a foundation model here, I mentioned a model that has been trained on broad data, typically at the internet scale and in a self-supervised fashion, and it can then be adapted to a wide range of downstream applications. Typical examples include vision language models, large language models, video generation models, and so on. NVIDIA actually has a catalog of ready-to-be-used foundation models on their website you can play with. Now, we're not quite yet at the level of one massive model that can ingest any sensor modality that can be adapted to any possible downstream use case. But this idea of a pre-training on the broad data and then fine-tuning on specific tasks has been proven very useful in a number of different contexts, to the point that oftentimes when we play with these models, we are left with the exclamation, wow, I didn't even know that such a model could do that. And the key reason why foundation models hold great promise for accelerating the development of robotic systems is that they provide an opportunity to tap into infinite scale knowledge that will help us in addressing auto-distribution events, very complicated events that might be very difficult to address otherwise. And to appreciate this point, I often say that it's interesting to make a parallel with how humans navigate the long tail of events when driving. So we, as humans, bring to the task of driving a lifetime of generalist experiences that endow us with a contextual and semantic understanding of the world that allow us to deal with difficult cases. Well, analogously, the hypothesis is that foundation models, which have been trained on multiple lifetimes of very diverse data, both from the driving, in the case of autonomous driving, domain, and crucially from the non-driving domain, provide us with an opportunity to bring this outside source of information to the robotics task at hand. At least this is the hypothesis. Now the question is how we can access this generalist experience for AV robotics application. And the answer is in multiple ways. Foundation models can empower several aspects of an AV robotics development program, from offline development processes such as auto-labeling and simulation, all the way to the onboard tech, like, for example, enabling new architectural designs or complementing existing algorithmic pipelines. So even though typically people, especially in an academic setting, prefer to focus on the rightmost branch, the onboard stack, actually foundation models provide a lot of opportunities also on offline development processes that, at least in an industry context, are extremely important. So in the rest of this talk, I'll discuss how we can leverage foundation models to boost the performance of the onboard stack. So actually, I'll be focusing on the right branch. And then I will discuss tools and techniques that can help us making a safety case about the deployment of these advanced AI systems in safety-critical contexts such as autonomous driving. All right. So let's start by discussing a little bit about opportunities using foundation models specifically for the task of autonomous driving. So early on, about a year ago, we started to investigate more quantitatively the question of what are the advantages provided by a foundation model empowered AV architecture. And to do so in a work called Agent Driver, we looked at a setting whereby a large language model essentially plays the role of an embodied agent that loosely replicates how a human drives. Basically, the LLM agent calls on demand different models, different capabilities, such as object detection, object tracking, motion prediction, and so on and so forth. Everything is orchestrated through a text interface, and then, based on all this information, decide what to do next. Of course, that's not how you would architect an autonomous driving in terms of autonomous driving stack. In terms of latency, it's pretty terrible, but it's more like a sort of a thought experiment to see what the potential advantages we have with such a foundation model empowered FineMath. And the results are summarized in the plot on the right. So on the x-axis, I show the percentage of in-domain data, so driving data that is needed to fine-tune the model. And on the y-axis, I have metrics that quantify how well the stack is performing. The specific metrics are not important here. And we benchmark the performance against a state-of-the-art model, at least in 2024, which was called Uni-8. So you can see that with only 1% of driving data, 1% driving data with respect to the data that Uni-8 was trained on, we can already achieve a performance that beats Uni-8. And there is no magic here. So basically, the model is using this outside source of information that comes from internet pre-training for the task of driving. With the idea that internet is cheap, driving data is much more expensive. So it seems that language pre-trained models are promising. So because of that, then we have investigated how we can best imbue language pre-trained models into an architecture, into an AD architecture. Of course, the design space is very large. There are many different ways you can architect an autonomous stack in a full end-to-end paradigm. And so for that, in a paper we presented at CDPR last year, we proposed a computational graph framework to model the general driving task. And through this framework, we were able to exhaustively evaluate several different architectures in terms of the necessity of a given module, its placement in terms of relative dependency, and also how to represent information. For example, we want to represent the information through in a rasterized way or more vectorized ways, and so on and so forth. And long story short, after an exhaustive experimentation of different architectures, we observed that one of the simplest possible architectures you can think of seems to be one of the most effective ones. This architecture, we refer to it as a paradrive. It entails a transformer that takes multi-camera images as input and produces outputs in parallel for 4 key tasks for autonomous driving, namely mapping, motion prediction, occupancy prediction, and motion planning. Importantly, paradrive follows the principle of train heavy and infer light. In offline training, all parallel heads are necessary and crucial, as the co-training of the different heads ensures that the learned features implicitly encode mapping or motion prediction type of tasks, which yields strong timing performance. But online, only needs to activate the motion planning head, which saves in terms of latency. In head-to-head comparison with state-of-the-art academic models, we show that these architectures run faster and also provide better performance. And what I like about this architecture is that at runtime, optionally, you can also infer through the other heads, like, for example, mapping or occupancy prediction, for example, in order to get out the signals that could be useful for marketing. Encouraged by these preliminary results, we further extended these archetypes with 3 core lessons from the design of the foundation models. First, the use of a scalable self-supervised losses, such as next video for language token prediction. Second, the tokens in and tokens out autoregressive transformer backbone, similar to what is used, for example, large language models and visual language model. And finally, the use of internet pre-trained foundation models for tokenization. So to evaluate this foundation model empowered design, we implemented a version of the model that uses a video generation as an auxiliary training class. Of course, at runtime, so when the vehicle is running around, you don't want to generate videos. This is only used at training time with the hypothesis that if a model can predict or generate a video, it can learn a very strong representation of the world. So to test the design, we use an in-house simulator based on neural rendering techniques. Here you can see the car driving around in a neural reconstructed word, you can see that is maneuvering reasonably well at intersections. Importantly, we were able to achieve this performance in a fraction of the time and resources that would be required to develop this capability in a classical AV stack. So we tested on the road. So these are some results from a fairly long test drive, several minutes with no human interventions. So this is in Santa Clara. And so this real-world driving performance confirms that the style of the training, for example, video generation, is quite useful. And also that our simulator is kind of correlated with the real world. And we'll get back to the issue of correlation between simulation and the real world testing later on in this talk. So going one step further, we experimented with using an internet pre-trained vision language model as the core autoregressive backbone. So quantitatively, on production grade data, do we see advantages with leveraging language pre-training? And the answer is yes. So on the right plot, I'm showing the training curves for a model that does not use a language model pre-training against one that leverages backbone that is pre-trained on the language generation. And as you can see, the blue curve, the one that leverages LLM pre-training, converges faster and to a better steady state. Both of them are important. So this indicates that language pre-training synergizes well with the task of driving, corroborating our earlier results. And we also conducted closed loop evaluations of this model, for example, in our neural rendering type of simulation. And so this model is also very promising from a productization standpoint, but this is the end of what I can discuss publicly. Instead, what I want to discuss publicly is that, of course, as all of you are aware, we are living in the past few months in the era of a shift from training time intelligence to test time intelligence. These models that try to leverage more test time compute have shown a superior performance in a number of complex multi-step reasoning tasks. NVIDIA has its own Cosmos reason model, and even a 1.5 billion parameter model achieves extremely competitive performance on the challenging platforms. And it is, promising because, up to a billion parameter model is something that is conceivable to be run at least on a chip for an autonomous vehicle. Now, this is encouraging because ultimately the task of driving or robotics more in general is a reasoning task. And of course, language allows you to expose your stack to multiple logical pathways. When you drive, you're always making sort of counterfactual questions, either implicitly or explicitly, about what if the pedestrian were to do X, or what if another car were to do Y, and so on and so forth. So that's what the reasoning model could give you as an advantage. On top of that, if a model can produce some sort of explanation about what it does, that signal can be used, for example, for monitoring purposes. And so all of this can be used very effectively as the basis for policy construction. Now, of course, the task of driving or robotics has a lot of structure. So we don't just leverage a large language model, test and computing naively, but we have to incorporate that structure into the chain of thought reasoning process. For example, grounding chain of thought reasoning traces into the physics and the structure of driving, like, for example, the map or the rules of the road, taking into account that, of course, the reasoning process is safety critical and has to happen within strict time limits. So we approach this by grounding the chain of thought process or reasoning process into the physics of the driving task. I'll show you later a little bit how we do it. And then by outputting different reasoning representations from meta actions that represent sort of a compressed reasoning output, like, for example, change lane or go straight and so on and so forth, to full chain of thought, to a full chain of thought reasoning trace. To obtain this kind of data at scale that you can then use for post-training, we need to carefully design a reasoning auto-labeling pipeline. You can't just rely on the human annotators, which is quite complex. is not just about tagging bounding boxes or trajectories. We need to generate an interpretable, grounded explanation of what's happening in a driving scenario. So to deal with this complexity, we break down this pipeline into 3 steps. In the first stage, we use rule-based methods to generate initial meta actions. Next, we bring in large vision language models such as VILA or EAGLE from NVIDIA. So these models analyze visual frames to identify critical objects and understand the scene dynamics. And then we pass all of these into a large reasoning model, so for example, DeepSeek R1 or NVIDIA reasoning, which leverage visual, vector, and the eco-motion context to produce a chain of thought trace. To show you how it's worked, here an example that work through the full chain of thought reasoning process. The systems first analyzes the surrounding environment and identifies the critical objects. There are 4 here. In this case, there is a vehicle cutting ahead. Then it will enter the reasoning phase and generate a guided chain of thought for what is happening, which is provided here, along with the meta actions that represent a compressed version of this chain of thought reasoning trace. And then at this point, you can use this high quality chain of thought data to fine tune your vision language action model. And our results are quite promising. So here we show that with respect to the baseline that I showed you before, by just post-training on meta action data, we can reduce trajectory displacement errors, which is one of the metrics used to judge driving performance, by about 20%. And then by further post-training on chain of thought data, we can dramatically reduce, we can dramatically improve, the lower the better, performance, specifically in the setting of challenging driving scenarios like complicated intersections and so on and so forth. So this is very encouraging. And to further investigate to what extent meta actions are linked to actually the trajectory that is, or the action that is produced by the vehicle, we pass these meta actions to the model as well to show whether we can control an end-to-end policy in a sort of discrete fashion, which is actually quite complicated. And we show that if we pass to the model the meta action straight, the model goes straight. If you pass to the model the meta action turn right, the model turns right. So we get a lot of controllability with this meta action. Now, of course, chain of thought reasoning, meta actions outputting is not the only way to improve or to leverage test-time compute. In another work that we have submitted recently, we look at the different ways of leveraging test-time compute through the lens of action sampling and then verification, more in a paradigm of generate and then verify. This work, which we refer to as a Robomonkey, essentially entails training or fine-tuning a vision language model on a synthetic data set of action preferences. And then online, we sample multiple actions, so we do a bit more work, and then we score these actions with this verifier. Of course, there are a lot of details that I'm not sharing here to actually cover other topics, but essentially the tidbit is that we see inference time scaling curves similar to what we've seen with large language models. So we see that by generating more action samples at the test time, so basically by increasing the test time compute, we can improve performance, so basically reducing the error with respect to an oracle. And we show that when applying these methodologies on top of widely used policies such as 5.0 or OpenVLA, we can achieve better performance in a number of domains. So there's much more I could say here, but my point is that actually test time compute seems to be a very promising direction for physical AI as well, as it has been shown earlier this year for these embodied large language models. Now, the topic of this workshop is safety, so let's talk a little bit about safety. Of course, there are a lot of concerns about feeding foundation model empowered AV stacks. Every time I talk to an automotive companies, you're crazy that you want to feed the VLA model, at least a Western company, to go to China is different. But my point is, at the end of the day, a vision language action model, or maybe you want to leverage a video generation model, what have you, is a large model for which, as a community, we have a lot of experience to build them with some safety assurances. Of course, there is no silver bullet for safety. Building a safe product really requires you to reasonable safety across the product lifecycle, from when we design it, basically building design time guardrails, for example, making sure that the model is trained on the safe behaviors, building runtime guardrails, for example, making sure we build the runtime monitors that monitor at runtime, autonomy stack, for example, at the input level or output level, or through other monitoring signals, and of course, at the validation time. Of course, safety is not a linear process, even though I depicted the design time and runtime and validation time guidelines sequentially. Is actually an iterative process where you go from issues that you find out to fixing the policy in a sort of a safety data flywheel. Next, certainly, several of our research results on the topic of AI safety have now been integrated within NVIDIA Helios. As announced at the last GTC conference by the CEO of NVIDIA, Jensen, Helios is a comprehensive safety system for physical AI safety, for which actually serve as its tech lead. And so what I want to discuss next are two topics. So among the many topics I could discuss here. So the first one, as it was also alluded to by the previous speaker, is to what extent we can use a simulation for validation purposes. So basically add validation time guardrails. Oftentimes simulation is cited as a tool that people can use for validation, but that's not so easy, as I will discuss in a second. Second of all, in a sort of a safety data flywheel paradigm, I will discuss how once we discover an issue, we can rebalance your data set or recurate your data set in a way that is principled in order to improve performance. So let's talk about whether we can use simulation for validation. Of course, simulation has been making a lot of progress in the past couple of years with new innovations in neural reconstruction, video generation models, and so on and so forth. That's all extremely useful for training and testing. But it's important to recognize that, for example, when you use, say, a simulator for testing, you're primarily interested in directional information. So basically, you're interested in understanding whether a given policy does better than a baseline. Specific numbers are important, but not too important. When you want to use simulation for validation, then you're interested in the absolute value on those numbers. Like, for example, you want to make sure that mean time between failure is some very low number for L2++ for autonomous driving, some crazy low number for L3, and so on and so forth. So then the question is how good the simulator should be in order to have enough trust in that simulator, enough confidence in that simulator with respect to the metrics that is metric value that is given here. And this is a very tricky question, because essentially it would entail using the real world data to validate the simulator. And it's even trickier because let's assume that you have validated the simulator. So somehow you're very confident that if your simulator is telling that your policies have a mean time between failure less than 1 in 10,000 hours, you're happy, okay. But let's assume that now you change policy. So your new policy actually might be sensitive to a different aspect of the input space for which you don't know if the simulator is a faithful replica. So you need to revalidate your simulator. So this doesn't seem to be too promising. So more pragmatically, in our recent work, we have looked at the related question that is that of, instead of using simulator only, why don't we do more work in trying to see how we can use real-world data and simulator in a coupled way, in a way that reduces the number of real-world data needed in order to achieve given confidence about the metric. So basically, how do you use more smartly simulation data as part of the evaluation process with real-world data? And to that, we turn to some Monte Carlo variance reduction techniques. So there is going to be a little bit of math, but please bear with me. So of course, validation encompasses several axes. But for this work, we focus on estimating the average value of some metric of interest, F, like, for example, mean time between failure. Now, currently, what you would do is to gather real-world data to estimate these metrics F, And then the Monte Carlo estimator will simply be the arithmetic mean of the samples that you have gathered from these random variables. And the variance of it is equal to the variance of this random variable, variance of f, divided by the number of samples. But the difference here is that what I'm estimating through Monte Carlo sampling is the difference of two random variables. So if they are correlated, a difference has much lower variance. Intuitively, if they are positively correlated, the noise in the same direction. So when you take the difference, the noise cancels out. And so that quantity has much lower variance. And actually, we can mathematically prove that the variance of this Monte Carlo estimator augmented with the control variant is equal to the previous variance multiplied by 1 minus rho squared, where rho is the coefficient of correlation between the random variables f and g. If g is a good surrogate metric, that is, your simulator is good. If g represents the metric as computed through a simulator, then you have dramatically reduction in the amount of data that you need to estimate your value. So with modern simulator capabilities, where we expect rho to be quite high, a reasonable question is to ask whether we can use simulation measurements as a control variance by pairing each real-world test with a simulated test of the same policy on a reconstructed scenario. And the key challenge here is that we don't know the expectation of G in this case. But the expectation of G can be computed easily by leveraging a SIM-only measurements. And these basically SIM-only measurements can be obtained through scenarios that maybe have been gathered through previous validation cycles. So if N is the number of real-world samples and K is the number of SIM-only samples, what we see is that now the variance takes the form of the last equation. K is the number of SIM-only samples, the idea that you can run simulation easily and inexpensively. As K goes to infinity, you recover the same formula, same reduction as before, 1 minus rho squared. So this is interesting because, as we show later, we're not placing any particular realism requirement on the simulator. Of course, the better the simulator is, the larger rho is, the less number of samples we need. So it's a very pragmatic view of using simulation for validation. Now, what if rho, even though you have made a lot of efforts in your simulator, is not too good? So rho is, maybe 0.6, something like that. Well, you can do something more. You can actually learn a metric correlator function that takes as input your surrogate metrics, so the metrics that's given by your simulator, foundation model features. This is another way we can use foundation models for advantage that basically embed the different properties of a scenario, and then learn a metric correlation function that gives you a new surrogate metric that hopefully is better correlated with the random variable we care about, which is f. And you can see on the bottom right there that we can readily learn new surrogate metrics that are much better correlated. So they are on the x equal I type of line. What important, so why do we use foundation model features in order to learn this metric correlator function? In order to learn this metric correlation function, you have to use some fraction of the paired simulated and real-world sample. So you're left with less real-world samples to do validation. So you lose a little bit. So you like to use as little as possible data to do so. Well, we show that in this plot here, even with the very minimal amount of paired real-world simulated data, we can learn a metric correlator function that is much more correlated with so on the green line, with the target random variable of interest, because we exploit foundation model features that already have some knowledge of how, for example, an average displacement error type of metric might correlate with the closed loop. So to make a long story short, let's assume that you want to estimate, in this case, a new plan closed loop metric that is expensive to run with just an open loop metric. Like, for example, average displacement error, it is a relatively poor metric. Well, we show that with our techniques represented by the green line, we can achieve a value reduction of about 32% by using 1,000 simulation rollout. And in general, we can see that by using this technique, we can get to the same level of confidence with about half of the real world of the expensive simulator samples that we would need. And this is for a surrogate metric, ADE, which is quite poor. So our expectation is that with this methodology, we can potentially achieve order of magnitude reductions in the number of real-world samples needed in order to validate a given policy for a given level of accuracy. This is very important because, especially in the end-to-end work, you need to do closed-loop testing for validation. You don't have a perception module anymore that you can validate with open-loop KPIs on previously collected data. So reducing the reliance on real-world tests is very important. This seems to be a promise. Okay, so just like in autonomous driving, validation testing are necessary to identify performance gaps. But what do you do when you find that there is a gap? Like now, broadening up a bit the discussion to robotics as well. For example, our end-to-end policy might lack precision to tie a cleat, or may choose a fragile pushing strategy when tapping a box with uncertain mass under the shelf, or sometimes might completely ignore other objects, dropping books from the shelf. So how we can systematically identify the root causes of this problem and correct for them? And the problem is that for policies trained end-to-end, we cannot just adjust the control logic. Instead, we have to reason about how AI performance relates to
Oops, that's me.
There was some echo. Okay, so basically we had to reason on how AI performance relates to the composition of your training data set. So for example, low precision might be the result of mixed skill levels of human demonstrators, or the result of some diverse strategies in demonstration data being more fragile, or there might be some spurious correlations that are picked up by your policy, like, for example, changing backgrounds here. So to systematically identify these root causes, our key insight is to develop methods to counterfactually reason about the impact of the inclusion or exclusion of training data with respect to policy performance. Concretely, we want to answer counterfactual questions about the training data, like how does the expected return change if we remove some demo from the training data? A process we refer to as data attribution. To do so, we perform data attribution using influence functions, which effectively compute a first-order sensitivity around reweighting a training sample. Specifically, we consider adding an infinitesimal epsilon on the loss of some training demonstration. So we consider a perturb objective where to our standard behavioral coding objective, we upweight one training sample through epsilon. Then we want to compute the influence of that sample on the policy performance. That is, we want to compute the change in expected return with respect to infinitesimally upweighting the importance weight. Okay? So in practice, computing this performance influence is not easy. So to compute that derivative is not easy. The notion of influence function has been around in the machine learning community for the past few years, but robotics has its unique features. In particular, the current data attribution tools only attribute an individual prediction back to training samples, where when estimating the performance of a policy, we have to reason about the outcome of a sequential decision. And second of all, we don't know the environment dynamics. So reasoning about these sequential decisions becomes challenging. So our insight is to apply tricks from policy gradients, if you are familiar with it, that allows us to decompose the performance influence into a tractable sum of the influence of training data on the action log likelihood of a policy. So it's a little bit of a messy formula here, but essentially is very similar to policy gradient computation that is used in order to compute that derivative with respect to action that I showed you before. So once we compute the influence of training demonstration on closed-loop performance, we can rank training data and curate data sets that remove, for example, low-quality data. So this provides basically a principal computable way by averaging rollouts to score the value of different data. And then you can decide whether you may want to remove some data from the data set or how to add data to your data set. In experiments, we showed that this allows us to prune low-quality samples or identify the most robust strategies in the training data and the test time distribution shifts, or root out spurious correlation, for example, in terms of the background and a number of books we have on the shelves. And we've shown that with this kind of retraining strategy, we can improve the performance of a number of state-of-the-art policies, like diffusion policies or Pi-0, by a significant amount. I really like the name Cupid, and the god of love. And the title of the paper is actually Cupid, curating data your robot loves with influence functions. I'm proud of the name. I didn't come up with a name, just to. Now, the last thing that I want to discuss briefly is that so far I've been talking about how we can achieve or actually how can we map guardrails to an autonomy stack that leverages foundation model. But something that's been a little bit overlooked so far is that foundation models have the potential to indeed improve the safety of an autonomous system in a different way. They can help with the data curation, they can help with sim validation, as we saw before. But one topic that I'm quite excited about is that they can help with the task of runtime monitoring, so understanding whether there is something anomalous in the scene, and if so, for example, give control back to a more classical stack, or maybe just not a contingency plan. So to be more concrete, this is an example that I've already been using a few times in my past talks. There is a case of an anomaly whereby you see that there is a truck that is spawning some traffic lights, make no sense. But then when we zoom out, we see that actually there is a truck with a traffic light that are misinterpreted by the Tesla autopilot as valid traffic lights. And this basically causes ghost breaks that are not only an annoyance, but actually they're a safety critical event because they can be rear-ended. But here is another example of a stop sign that is printed on a billboard that, again, is misinterpreted by the autopilot as being a legal stop sign. And so there was this customer that was very upset because every time his Tesla was driving by the billboard, the Tesla was slamming on the brakes. So I refer to these anomalies as semantic anomalies because they're due to a very unusual combination of in-domain situations. And of course, I mean, by now, you should be familiar with the spirit of this talk. One possible way to address this issue is by leveraging foundation models and their auto-distribution capabilities. They've been pre-trained on internet-scale data, so in principle, they've seen everything. So we actually saw that there is a lot of potential in using foundation models for anomaly detection as far back as in 2023. Of course, the problem of using foundation models for anomaly detection is that querying the foundation model is expensive computationally, and typically for runtime monitor, you want to have a very lightweight algorithmic pipeline. So in more recent work, we have been looking at leveraging foundation model embeddings for anomaly detection and only query a foundation model if an anomaly is detected. So basically adopting a sort of fast and slow type of reasoning framework whereby you reason very fast about whether there are potential anomalies, and then you slowly reason about what to do if an anomaly is detected. A little bit how I would say people drive. Typically, you don't think when you drive, but when there is something weird, then you slow down the dynamics to buy yourself some time, and then you think about your contingency plan. We're running out of time, so I'll be a little bit quick here, but basically the idea is to build a data set of nominal experiences that are compressed in a foundation model embeddings. It still retains some semantic knowledge. And then at runtime, what we do is to observe a scene, compute its embedding, compare the embedding to those from the database. And if the embedding is farther than a given threshold, then we declare that there is an anomaly, and then we query a full-blown foundation model to reason about a contingent plan. Otherwise, we keep driving as normal. So we recreated the scenario that's stopping on the billboard. On the left, you see a stack with no runtime monitor that stops at the stop sign. So it's failure mode. You should have stopped the stop sign. Without a methodology, actually, the model understands there is an anomaly, but then it understands that it can keep driving because the stop on the stop sign is not a legal stop sign. To show you how this works, we first use a fast anomaly detector to detect the stop sign on the billboard, but it's in terms of its embeddings. And we can do that very fast in a matter of a few milliseconds, depending on the specific model that you use. And then at runtime, if an anomaly is detected, in this case, we were using GPT 3.5, which was running rather slowly at about 3 seconds per generation. But all of that is orchestrated through a modality control controller that also accounts for the delay that will occur by sampling a foundation model. So as an emerging property, you have that the vehicle slows down its dynamics in order to account for this delay. We showed that actually this works pretty well. There are many things that can be done in the future to improve it, like, for example, reasoning about multi-frame observations as opposed to just one observation. Of course, many anomalies have a temporal connotation, so that's why you need to reason about multiple frames. Or fine-tuning the model on AV data. So here we use the model basically zero shot. We have applied now this style of reasoning in a variety. We have extended in a variety of ways, like, for example, by using visual language models to inform about what specific contingency plan we may want to execute, basically planning in foundation model informed safety cost function space, or reasoning about physical properties. But here you see some bits. I think the one on the right is interesting. So there is a drone that is trying to land on a box. And with a visual language model, we understand that with a downwash of the propeller, the box will flip. And so you have to approach it from the side in order to avoid that the box flips. So that was kind of interesting. And it's quite powerful. So we have applied it to a number of different domains, like the construction robotics, marine autonomy, space robotics. On the left, you have quadruped that is walking around construction environment, detecting oil spills and all of that in real time. So all of this to say that foundation models can be applied more broadly also as runtime monitors as an additional ways to add intelligence to your stack. If you're interested in auto distribution for robotics, we have a great paper, actually dated by now. So let me conclude by saying that foundation models offer great promises for autonomous robotics across development process. On board stack, we haven't talked much about offline development processes, but a lot of opportunities there. As part of onboard performance, they can also be used in different ways, from improved optimization all the way to backward retraining and scalable self-supervision. What we're particularly interested in now is in a better understanding the opportunities offered by the shift to test time intelligence in different ways, like channel clock reasoning or more actual sampling and so on and so forth. And for safety, there is no silver bullet. I showed you today a couple of results related to how to leverage a simulation for validation and how to implement a safety data flywheel in a principal manner through influence functions. But there are a lot of other exciting developments. And yeah, if you have any questions, I'd be happy to answer that.